Okay, watch stream.
Hold on, I'm gonna close my door real quick.
Okay, that's fine.
Okay. All right. Hello, everyone. I'm here with my friend Ethan. He asked me about some ideas in like renormalization and renormalization group, and I thought it would be apt to make a video about it because, to be honest, this is one of the most impossible subjects I have ever learned in my life, and I just wish it had been explained a little differently. So I'm going to give my attempt at an explanation of renormalization. This is going to be from the viewpoint of like Peskin and Schroeder style. So it's going to be more for high energy people, but really this is an introductory view of it. So it's important to understand this even if you're in condensed matter or like lattice physics, because it's just such a foundational understanding can be obtained here. So if you're here, you've probably already heard of the general idea of renormalization. So it's this idea surrounding vaguely, very vaguely, canceling infinities, something about divergences of diagrams. You might have also heard it as a flow of a coupling constant. You might have also heard, oh, the mass just gets renormalized. And I just want to say that, once again, this is a difficult subject. That people pretend is easy when they speak. Okay, if you're one of the people who's read a paper and heard, oh, it's just a renormalization of the mass, it's just a coupling renormalization, that just gets renormalized away. Inside of those phrases, there is an absolute insane amount of things being contained and swept under the rug. So don't feel alone if you've been sort of intimidated by that phrasing. This is a really difficult subject, and it takes a little bit of time to learn. Okay, we're going to start our journey here on a topic that initially I thought was dumb, but then I really realized once I was really struggling with the subject, it's actually the key to understanding the whole thing. So this is going to come from more or less chapter 7 of Peskin and Schroeder. I believe this is about section 1 right here. I'll try and do some loose markings of which section is which. And we're going to talk about something called I believe it's the Kähler-Lehmann spectral representation. I'm just going to call it the KL spectral decomposition. And again, at first glance, it seems like this will be totally useless to us, but it's actually going to be totally essential in understanding the basic conceptual idea of renormalization. So the idea of the spectral decomposition is that the true amplitude for propagation between point y and point x
So I'm just assuming you just left out the time ordering operator, right? Or is that
yeah,
just
time ordering. We're not going to like be too concerned about nitty gritty, but yeah, time ordering is left out. Um, for
that?
anyone watching who isn't acquainted with notations, x and y have the time included in them. So there are each 4 vectors. So this is the standard object in QFT, obviously. So the spectral decomposition says that if you compute this, which is a sum of diagrams, okay, let's say we're working in phi to the 4th theory. So it says the way you obtain this is by doing as a sum of diagrams as just a basic line plus, this is not phi 4th, sorry, let's say phi 3rd theory for now, plus this, and you do the sum of these 2 diagrams, and that gives you the true total propagation amplitude. And again, this contains the subdiagrams or the individual diagrams. and each of the subdiagrams is a specific way the total process could happen. Okay, what the spectral representation says is that if you add up all the diagrams together, the statement of the representation is that you had better get something, and I'm going to leave out factors here, you're going to get something that's I over p squared, depending on your conventions, plus or minus p squared minus m squared. And I'm going to call it m true squared. Okay, they basically say if you compute this diagram and you get that it has the form I over p squared minus 9, the true mass of your particle is 3. Importantly, again, you have to compute the sum of diagrams and compare these two. So compute sum of diagrams. And after you've computed the sum, then you compare these two to read off the true mass. And extremely importantly, let's say this theory had a Lagrangian like this. I'm going to call this m0, the Lagrangian mass or the bare mass. This number, the true mass, is generally not going to be the same number that was in the Lagrangian. And I'm going to write this in red here, core concept, core idea. This true mass generally won't be the m0 number that appeared in the Lagrangian. And I'm going to box this in my handy Galaxy color ray pen, because this is the central idea. Yes, Ethan?
Ask a quick question. So in like let's say it just were limited to like phi squared, like for free particle, then it would be the same, right? Or would it not? Or is that still?
Yeah, so just to restate your question, Ethan asked if there wasn't like a phi cubed term in here, would it be the same? And the answer is yes, because at that point there aren't any other diagrams that you could even have.
Oh, right. That makes
yeah. But when you have things like phi cubed, phi to the fourth, these other diagrams are going to modify the actual form when you sum them in.
All right, that makes sense.
Yeah. Cool. And again, I am leaving out some numerical factors here, like some integrals, some 2 pi's. But this is all about the conceptual side of RG, so we're going to ignore that for now. Okay, now I actually lied a little bit just to simplify. So it turns out the KL spectral decomposition, it actually says you're allowed to have an overall multiple up here called Z, and you are able to, similar to how you were able to compare the value of, the highlighter doesn't work too well here, you were able to compute this number and then you compare your result with this form to read off the true mass. Similarly, you can read off this number that they call Z from the sum of diagrams. So as an example, let's say I computed the sum of diagrams and I got that my sum of diagrams gave me an answer of 5/7 I over p squared minus 2/3 m0 squared. And if you want, the plus I epsilon can stay in there too. Let's pretend I computed the sum of diagrams for my given theory using a Lagrangian with the number m0 in it. for the mass, and I got this out. This is a computation you have probably already done before. In this case, you would look at this, you would identify, from comparing it to the spectral decomposition, you would identify that the true mass is 2/3 of the number you put in the Lagrangian. Again, it looks like the number you put in the Lagrangian is the mass because it appears in front of phi squared, but it'll be adjusted due to other processes. And similarly, you can read off the value of z from this to be 5/7. Okay, and this is a really, really key conceptual step here. This is an example where z and m true were just common numbers. As you get more into the weeds, you'll see that m0 and m true may be related by more exotic numbers. They may be crazy functions, like m true might be the arc cosine of m0, or it might be m0 plus 50 billion, or m0 plus infinity even. But this is a fantastic place to stop and come back to if you get confused later. Just pretend all those crazy functions are easy numbers. Okay, we're going to do a case example coming out of QED to actually compute this quantity, this sum of diagrams, in a real theory. And this is going to be probably the most important section of this lecture, besides renormalized perturbation theory, which is much later. Okay, so the case example is QED, where I'm going to compute the total amplitude for an electron to propagate. And this could occur either by straightforward propagation or, to lowest order in perturbation theory, it could involve this other process as well, where there's a photon loop that occurs. Okay, and it's just going to be our task to compute what these things are. So I won't actually do the calculation here. I'll just read off answers from what's known. So this one right here, depending on your conventions, you may see it as I over P slash plus M. I'm going to write it in the non-matrix form with the matrix upstairs. Okay, and then the second diagram, again, if you're here, you probably already know how to, in principle, compute this, or at least write out the rules with integrals. So the left edge of the propagator, this is going to be one factor of p. And again, p is we're computing the amplitude assuming a momentum of p. If you're being really strict about it, we're computing the Fourier transform of the amplitude to propagate, but all those details we're leaving out. That way we can focus on what's actually at issue here. Here's another factor of that same free propagator. Okay, and this bit in the middle, we're going to not actually compute it. We're going to give it the name minus I sigma 2. So this is a messy expression involving P and M naught. Okay, and oops. And again, all we're trying to do right now is compute this diagram. So far it looks pretty bad because we have this giant expression with two things added together, and the instruction to read off the true mass and z is that it should look like this. Now there's a trick that we're going to do, which you'll do pretty often, and it's done so often that often people skip it entirely and just write down the answer knowing that you will do this anyway. The trick is we're going to geometric series sum this crap to bring this into the denominator, basically. I'll illustrate in full what we're actually about to do. So again, the idea is to read off the true mass. Oops. We want to compare to something of this form. But the issue is we have a sum of terms and this is a single term. So we need to massage this into this form. And the trick is you use geometric series. Okay, you notice that there's a factor of IP, and then basically I only drew it up to like first non-trivial diagram, but for every other additional diagram, vaguely, you're going to get another factor of this in each. So the geometric series, like coefficient is going to be, or sorry, the common ratio in the geometric series is going to be something like this expression. So again, vaguely what that's going to do is you're going to get the p/slash term out front, and then 1 over 1 minus the common ratio, which is vaguely going to be that ugly expression for the first non-trivial diagram, sigma 2, which is this horrible, horrible like integral expression right here. Or sorry, I didn't write the integral, but it's the expression corresponding to this chunk of the diagram.
And this is only second order, right?
Yeah, so this is only doing the first, second order in perturbation theory. We're only dealing with the basic line plus one non-trivial diagram.
And so,
Hypothetically, you could compute this with even more like loops involved, but we're not going to do that yet.
all right, but okay, yeah, I'm sure. Yeah, let's just keep it simple now.
Yeah, well, I'll roughly explain what you do when you go to higher order later. It isn't too much worse. Also, at this point, I just want to point out that this was for a scalar. The KL representation said it should look like this. And this is for an electron propagator for a fermion. So what the KL representation says for a fermion is that to read off the true mass, it's Z over p/slash minus the true mass is what you expect to get. So again, this is just because we had p squared with no p in the denominator, or no p in the numerator there. But here we're computing something involving fermions, so we have a different form. So anyway, we're going to compare our sum of diagrams to this form to read off the true mass and Z. And if you actually do the computation for the geometric series, what you get for the value of this mess that we're going to compare to this ideal form is that you get I over p/slash minus m0 minus sigma 2, and sigma 2 has a p in it. Okay. Now again, we're going to compare these two to read off the true value of the mass. Now, at first glance, if you're not careful, it looks like m0 minus sigma 2 would be the new mass, but that's actually not the case because sigma 2 is a function of p. So like you'd also be tempted to say that z would equal 1 because there's nothing upstairs. but we need to organize it in like a expansion around a pole because P appears in multiple places in the bottom. So we need to rearrange it to truly have the form on the left.
Mhm.
And if this isn't totally clear to you, Peskin and Schroeder actually has a decent discussion of this. So the pole here is no longer at M0. Again, I loosely earlier said we should just be able to look at it and tell, but in truth, what the spectral representation says is wherever your wherever your full sum of diagrams has a pole, that is the true mass. So wherever this has a pole, according to the KL representation, that is the true mass. Okay, and if you actually do the calculation, again, Peskin and Schroeder goes over the nitty gritty of how you do it. It's not too hard. You find that the true mass is M0 plus sigma, which again, sigma evaluated at P equals M0. And again, sigma, it's a super ugly expression, but at the end of the day, it's something like 50 M0 plus 5, something like that. So that gives you your relationship between the real mass and the mass that appeared in the Lagrangian. Similarly, so sort of how like the instruction was comparing with the KL representation, find where the pole is, that defines what the true mass is. What defines Z is a little uglier. It's like what appears in the numerator in the 1 over P term in the expansion of the propagator around that pole. So it's like what defines Z is it's the residue, i.e. the numerator. If you rewrite this or if you expand this about the true pole, and again, Peskin and Schroeder actually shows you why it should be this calculation, but the instruction is that, or the result is that if you do the expansion, what you find in the numerator is that the number that appears in the numerator is 1 plus the derivative of sigma with respect to P evaluated at M0. Again, all this is saying is that here's a horrible expression involving some numbers, and it's going to appear upstairs in your true propagator. And by comparing it with a known form of a propagator summed with all diagrams, you can read off what Z is. Ethan, do you have any questions you want to ask about that?
No, this all makes sense.
Okay,
I mean, I'm mostly familiar with this stuff.
okay, perfect. Yeah, this is more for people who haven't seen it before, and to paint a full picture with my notation. Okay, now here's an issue I've been sweeping under the rug. I told you sigma was something like 50 M0 plus 3. The issue is that sigma actually is infinite.
It's not very good.
Yeah. If sigma were something like 5 M0 plus 2, it would be all well and good. But, and honestly, that's the way you should always think about it. Just literally ignore the fact that it's infinite in most of your thinking about what sigma is. It's just some number of M0
So
times 5 or whatever. But sigma,
actually,
actually, if you go in and compute it, it's infinite. It involves something like integral d4k over k squared. And if you actually evaluate this in like polar coordinates in k-space, it's something like integral from the radius in k-space. I might not get my powers right here. I think this is right. It's something like this. So it basically comes out to infinity squared. So just as a placeholder, it's still infinite, but we're going to call the upper bound lambda. So we're going to say it has a value of, oops, I don't know how that just moved. We're going to call its placeholder value lambda squared. Yes, lambda is technically infinite, but we're going to avoid the issue of infinities in our like numbers for now by just calling it lambda with the understanding that lambda is really big and is technically actually infinite. But all the calculations we've done so far are still okay.
So when you say sigma here, that's the full sigma, right? With all the terms.
Yes, okay, this is actually something I should say. So sigma here, so I'll put this as like a side note. So sigma above was the piece of the diagram corresponding to this. We cut off the legs that used to be here and here, and it's just this annoying part in the middle. The reason I used a 2 is that if you choose to compute this to higher orders, so if you include more diagrams, such as this ugly guy right here, more things enter into the geometric series. So in that case, sigma 2 might be, sorry, I should just say sigma. Sigma might be that plus, I might have to draw some crazy diagrams here,
That's
plus
that's.
that.
I think that's. They're not. Those are the same. It would be like if you move them so that
No,
they
like
overlap.
if there's two opportunities for momentums to exchange here. In any case, it's the next non-trivial diagram
Yeah,
in
sure.
the next order in perturbation theory. This may not be a legitimate diagram. I was just sketching.
I don't think it is, but
Okay, yeah, that's fine. So something like this. And if you go further, again, Peskin and Schroeder has a pretty good discussion. If you've understood what I've done so far, you can go back and look at the book for a better understanding now that you know what's going on. They have a pretty good discussion. Sigma technically is like they call it the sum of one particle irreducible graphs. So it's a subset of these weird graphs in the middle. It's basically like the sum of distinct problematic graphs. Like this one is considered irreducible because you can't cut it in half. Actually, I guess I was wrong. You can cut this one in half so it doesn't count as irreducible. It would be really problematic diagrams like this. I think that would count as
yeah.
irreducible because you can't cut them and get two equally valid graphs. But anyway, this is just for higher orders in perturbation theory. So this is all as a side note. But Peskin Schroeder has a good discussion on this. This is how you would, in principle, do it. You would compute, instead of just this graph, you would compute that graph and add it to some other troublesome graphs. Okay. Next thing I want to talk about is charge renormalization. Or actually, before I do that, I suppose I should just make an observation here. So we had this issue that sigma is actually infinite. It's either like lambda squared or maybe log of lambda. Either way, it's infinite. But the issue is actually not an issue. Okay, we're going to go over it more in later on, like specifically why it's not an issue when we talk about measurable quantities and phrasing results in terms of known measurable finite numbers. But just as a general sketch here, we had something like the true mass was the Lagrangian mass plus sigma, which we now know is some infinite number. As a very rough idea, and I'll clarify later like how this actually works and what it actually means, the rough idea is that m0 can be a number with a infinite part in it as well. Basically, m0 can contain a minus lambda squared. Yeah, come in. Yeah, Ethan, I gotta go start the test right now, so I will cut this
Yeah,
out of
that's
the
fine.
video later. I'll only be like 2-3 minutes, so let's just take a break.
Okay, it's
Yeah,
good to
all
me.
right. Pause. All right, I think we're live again. Okay, so we are going to go on to charge renormalization now. And roughly this is section 5 of chapter 7 in Peskin and Schroeder. And also be aware, some people will call charge the coupling, or I suppose it's actually probably more correct to call it the coupling than the electric charge. But for us, it's going to be the electron charge. And we're going to talk about how its value may not be the same number you put into the Lagrangian in front of your E psi A psi bar term. Okay. Okay, so there's something, I suppose it isn't exactly the Keller-Lemon spectral representation. I don't think it has a name here anymore, but there's a general expectation that the true value of all propagation, all pathways a photon can take, so roughly this is like A at one point and A at another point, very roughly speaking, that this should again be, so I'll put like an equal sign, I'll say like expected slash defined to be, and again, this is the analog of the KL spectrum. So just like there, it said the sum of all diagrams is going to take a form that looks like this, and you read off the true values of M and the value of Z from it. It says that this diagram should take the value, or sorry, the sum of all diagrams should take this value. And for whatever reason here, they use Q for the momentum in instead of P. Okay, and again, what this is saying is if I compute all diagrams up to a certain order of this form, and in the case of this is in QED, by the way, I should say. So new action, new diagrams are going on. So I'm actually computing this left-hand side, the sum of all diagrams up to a certain order in perturbation theory, which includes the normal plus the one with the intermediate loop. And whatever number I get out, I can draw circles around things to identify the true mass and to identify what Z3 is. Okay, if you compute it in the exact same way as before, you basically find that the first term is minus IG over Q squared. This term is minus IG over Q squared times some super messy loop that we call pi, times another factor of IG. Okay, so pi of Q involves this loop in the middle. So pi of Q is this horrible loop. And it depends on the total momentum being injected and leaving at the end. I'm going to be really, really messy and not care about which indices are contracted. This sometimes is defined to have indices. I think technically this should be like pi with two indices on it, and you define it as being some function of Q with indices times this thing without indices pi. But I'm not going to care about that. That's all like nitty gritty details. The thing you need to understand is that capital pi corresponds to, in some way, without indices maybe, this horrible diagram in the middle involving the fermion loop. Okay, and just like before, we're trying to compare it with this, the known form, the expected form. So we could identify what M true is and what Z are. But again, we run into this issue of we're adding up terms and we should be having one term. So we're going to use this geometric series idea again. So if you use geometric series on this, what you get is I G mu nu, sorry, maybe you get minus I G mu nu over Q squared. And then again, using the geometric series, you get this. Again, as of right now, pi is some weird function of Q. Maybe it's like, oops, maybe it's 2/3 Q squared minus 50Q plus 5. Pi is some awful function of Q, and you can compute what it is by computing the fermion loop, but you don't really care. You just leave it as a pi. And you know that you can calculate its value if you need, but it's some awful function of Q. And this is the direct analog of sigma above. Honestly, you could call it sigma and no one would complain. Again, the only difference is technically there's some index stuff going on, but we're sweeping that under the rug. Okay. Oops, I just realized the mic was on the table, so I'm thinking it should probably still be okay volume-wise, but I'll clip it back to the normal.
It was a
Was it
little.
okay?
It was fine. It was a little quiet, but I mean,
Okay.
but it's
Okay.
fine now. It's a lot better.
Yeah, now it's strapped back onto me. So sorry, listeners, you might have to turn up the volume to get that last part correct, or to hear everything I said clearly. Could you hear what I was saying still, Ethan?
Yeah, no,
Okay,
absolutely.
okay,
I mean,
that's fine.
I would have said something if I couldn't hear you.
Okay, it was just a little further away.
Yeah, that's all
All right.
good.
So here's our actual result for the diagram, or for the sum of diagrams for photon propagation. So at this point, we can compare with the expected form, which is this, and try and read stuff off. Now, as before, M true, you get it from the location of pole in this giant blob right here, because that's what the general expectation says. It says the denominator should have a 0 when you put Q equals to whatever M value is the real pole. And if we look at the actual result that we have here, the denominator is 0, so there's a pole. At Q equals 0. As long as pi at Q equals 0 is not infinite, in which case we'd have to do some weird infinity times 0 limiting case stuff. So this tells us the true mass of the photon is 0.
Well, that's good.
Which is really good, because if it wasn't, that would be pretty bad. All right. Analogously, to get z, you have to like expand about the pole, and then the result is z, which, by the way, z in general might depend on the momentum that you're putting in. So like z might change depending on the q of the diagram. So I believe Peskin-Schroeder's notation is z of m true, even though m true and m0 will turn out to be like infinitely different than each other, you're allowed to do this for black magic reasons. And I should say this m here is the m of the photon. What you get is that z is 1 over 1 minus pi evaluated at q equals 0. Okay, so congratulations, you just read off the true mass of the photon, not the mass that was in Lagrangian, but the true mass from its physical behavior. Right? This is like the physical, all possible ways photons can get from one place. This is actually their true mass. So you read off their true mass is 0, and you read off their z factor. Okay, now, if you come, by the way, I think I forgot to mention something. Technically, I think you expect this to be equal to, okay, here's like a little bit of a sticky issue, and Peskin-Schroeder, I think, will talk about this a little bit more. But so I think technically you expect it to have this form of Z3 times whatever charge you put for the electron in the Lagrangian. So there's a little bit of like carelessness here by me for exactly where you should define an E0 to be. But the general idea is that since the propagator with the additional electron factors in it again, each electron factor comes from the two vertices here. Ooh, I think my computer is going to start overheating here. Let me see if I can aerate it somehow. This should be good enough. What is traditional is to sort of absorb z into the epsilon or into the E0. So people like to define and by the way, the reason people call it Z3 is it's like the Z for the photon particle. There's a separate Z for the electron. This is the Z for the photon. And people will absorb the Z for the photon into the E0. And specifically, they're going to define it as Z3 square root of Z3 times E0 equals E true. Okay, and importantly, Z3 is defined to be 1 over 1 minus pi at q equals 0. Okay, you reference a specific value of Z3 at a specific momentum to define the true electron mass. Okay, now the thing is, when you try and use this definition for Q that are not near zero, additional factors will appear in this expression. So if you have your expression E0 squared G over Q squared 1 minus pi, okay, and again, this is the expression you get from the sum of diagrams. If you write this in terms of E true, you get this. And where this extra factor comes from is, again, from making the replacement of E naught is replaced, E naught and part of this expression in the denominator get replaced with E true, and E true has this business where it involves 1 minus pi at Q equals 0. Okay, so this is the notion of a Q squared or a Q dependent electric charge, where basically the value of the propagation for the photon, it changes as you mess with Q in a way that isn't just the simple 1 over Q squared from the Fourier transform. Again, really, technically, this isn't like the electric charge changing. It's more like the amplitude for propagation for the photon has an overall multiplier, this z factor that we chose to absorb, that depends on momentum, since we related the true charge to the Lagrangian charge at a specific reference value. And as we move away from that reference value, pi of q versus pi of 0 are now no longer the same number. And again, this will become more clear when we do renormalized perturbation theory, why we do this. In bare PT, charge renormalization is a little bit more confusing. And what's nice about this is that actually, again, pi was infinite. However, pi of q minus pi of 0, each of them is infinite. The infinities cancel out and you just get a nice number.
Nice.
Which is super clutch on the part of renormalization. Another side note before we get to the really interesting stuff is that beforehand we had this placeholder for, it was sigma before, but now it's pi because it was infinite. So we would say pi is lambda squared. As a placeholder in our calculations. But it turns out you don't want to do this. In QED. And the reasons are a little fuzzy for a first-time learner. You'll often hear it violates the word identities. So it doesn't play nicely with a symmetry. Ward identities are, in a nutshell, I'm not going to go into it in too much detail, but ward identities are your QFT diagrams and QFT amplitudes. They aren't free to just be any old function. They have to share the system's symmetries in correlation function mode. So for example, if you have the U1 symmetry, so you're allowed to rotate by a phase, symmetry of the action, the QFT amplitudes, when you add them up, they also need to respect something similar to that. And if you try and compute sum of amplitudes using this lambda squared method, it turns out you don't get the proper relations between the amplitudes. They don't share the symmetries that the classical theory does. So QFT amplitudes need to reflect the symmetries of the classical theory. Yeah, you can come in. One sec. I'm gonna see this.
Yeah, it's all good.
Yo, did you just finish up? Yeah. How was it? Let go. You did well. All right, we're back.
All right.
All right. All right. So just as a continuation, so you don't want to use this lambda placeholder. And again, you'll learn more about this in your field theory class, but instead, you'll parameterize the divergence by saying it's like you'll mess with the number of dimensions you do the calculation in, and you'll have 1 over epsilon, where epsilon is like 4 minus the dimension, will contain the infinity, I'll say. It will contain the fact that the amplitude is infinite. In any case, it's still an infinite number. You're just storing the infinity in a different way, and instead you take epsilon to 0 instead of lambda to infinity to get the true value. Okay, so again, charge renormalization, a little hard to understand from the bare perturbation theory perspective. We're going to learn renormalized perturbation theory, which is a lot more clear.
Awesome.
All right, so here we're in chapter 10, section 1. I just want to go over some quick laundry here. So they call this the counting, like power counting of divergences. And this classifies theories into 3 groups: super renormalizable, non-renormalizable, and just barely renormalizable, which is just called renormalizable. I don't know why they didn't pick different names, but so super renormalizable theories are the ones where if you go high enough, or actually first I should say this, the superficial degree of divergence of a diagram, for example, as a case example, let's take, actually we need to do QED for the formula I have to work. Let's say a diagram like this. The degree of divergence of this diagram, there's a formula you can do to compute it. It's the space-time dimension plus this number times the number of vertices in the diagram minus this times the number of, I believe this is photon propagators. It could be external photons. And again, I forget if this is internal electron lines or external electron legs, but this number will tell you if this diagram contains infinities or not. And depending on the number, it may tell you if it goes as log lambda or lambda squared, or if it does not have lambda in it, it would not have a degree of divergence that's positive. And you can classify theories based on what kind of diagrams they have. Are there many, many, many diagrams that are infinite? Is there a finite list? Are there none? And that's what these three things do. So super renormalizable is that okay, well, I guess it's a little more subtle than that. It's that there's only a finite number. So I'll say only 4 or 5 as a case example. There's only 1, 2, 3, 4, or 5 or something diagrams that diverge in the whole theory. So even if you draw diagrams with like 15 vertices, and there's all this crazy crap going on, out of all the diagrams you could possibly draw with any number of vertices, there's only 4 or 5 with divergent terms. Non-renormalizable means that as you add more vertices, every diagram is going to diverge. So at high enough number of vertices, every diagram diverges. And renormalizable theories are that they're sort of finicky to state precisely. Let me make sure I state it clearly. Only certain amplitudes are going to diverge at each order in perturbation theory, but they happen no matter how many vertices you have. So this is to say that there's a divergent diagram when there's 2 vertices, which would be a diagram like this. As you add up to, I don't know, 15 vertices, it's not that every diagram diverges, but there's still a list of diagrams, a finite list of diagrams that diverge at that order. Do fact check me on this. I think I have this straight, but I don't have very good notes on this, I realize, so I'm kind of going off the top of my head. But vaguely, this is what it means, that super renormalizable versus non versus normalizable. It just distinguishes how many badly behaved diagrams are there in the theory. Are they infinite? Like, is the theory plagued with them at higher levels in perturbation theory, like non-renormalizable, or something else? Most theories of interest are renormalizable, just barely. Okay, now we get to the meat of renormalization. And again, this is chapter 10, section 2. This is renormalized perturbation theory. And this is compared with bare perturbation theory. Before. Okay, so just as a reminder, before we used a Lagrangian with these parameters in it that didn't turn out to be the true mass. And we read off what the true mass was. by reading off the sum of diagrams. Okay, once you have, I guess I didn't say this before. Once you have the value for m true equals m0 minus, or sorry, I'll say m true equals 3/5 m0. You can substitute m0 equals 5/3 m true in all your computations. And this will miraculously like cancel out any sort of infinity by just writing them in terms of the true mass. So for example, if you compute the 4-point function, and previously it had a number you didn't like in it, like let's say this is the result you got and you don't like the fact that there's an infinity up top, well, the sort of miracle of this all is that if you computed the 2-point function, you would have found that m0 squared plus lambda squared is m true. So your result here would actually be m true over p squared. Sorry, I should have written the extra m squared. So you can do that substitution after you found m0 in terms of m true and just make the replacement everywhere. And that gives you the true value of the diagram expressed in terms of multiples of the true mass instead of the Lagrangian parameters. Okay, that's how you do it in bare perturbation theory. In renormalized PT, we're going to mess with the Lagrangian before starting the calculation. Okay, we're going to split the Lagrangian mass into, we're going to define it as being split into the true mass plus this thing called delta m. And almost by definition, this is the difference between the true mass and the Lagrangian mass, m0. So before in your Lagrangian, if you had m0 squared phi squared, now you have m true squared phi squared plus delta m, or sorry, I suppose, I actually think you split m squared into m true squared plus delta of m squared. Again, this is a notation difference between m true squared and m0 squared. So in this case, your Lagrangian splits into this plus this. So you split the Lagrangian term into the true mass term plus the other part. And you call this delta the counter term, the mass counter term. Oops, can't spell. Counter term. And again, this is what happens in your Lagrangian. Okay, also what you're going to do is you're going to rescale in the same way that we split m beforehand. We're going to rescale phi. We're going to call phi true is going to be defined as 1 over square root of z times phi original. The motivation for the square root is in the KL representation means something like this. So we sort of absorb a factor of z into each factor of phi. That way, if we instead of phi original, we replace each factor of phi original with phi true. Each phi original yields a factor of square root z. And again, KL representation says this is how it must look. The z's cancel from both sides. So what you find is that if you compute the correlator of these phi true fields, you had better get 1i over p squared minus m squared, if you picked the definition of the true field correctly. Okay, if you make all these replacements in the Lagrangian, and also you define the coupling constant, which before was E, I'm going to call it lambda because we're going to do phi 4 theory here. You define the number that's in the Lagrangian as being the real value plus the difference in the true and the bare value. If you make all these replacements, you get that the QED, or the phi 4 Lagrangian, is something like and I should remark here, z true is defined as being 1 plus delta z, or delta lower z. Okay, so here are all the counter terms, and here are all the non-counter terms. Okay, what we're going to do now is we're going to use this Lagrangian to compute a sum of diagrams where the ones on the end are technically the true phi's that we're going to use, which is nice because this is what our Lagrangian is phrased in terms of anyway. So we're going to compute that, and we're going to write out the answer we get. Now we have to remember that before we just had to use the phi to the fourth diagram, but here there are basically additional interaction terms, basically additional diagrams that we have to insert in. Such, for example, this diagram right here contains a interaction of phi with itself. So it's like an attachment point between the two phi's that can occur here. And the Feynman rule is that you would insert, I forget if the 1/2 goes there, but basically the Feynman rule is that this diagram contributes a multiplicative factor of delta m in the same way that a vertex might yield a factor of lambda. Okay? So we compute the diagram with these additional counter term interactions, quote unquote. The interaction of vertices. Okay, so in this case, what you're going to get is it's the free diagram plus the mass diagram plus, I wasn't very careful here in phi third versus phi to the fourth theory. So I will just say schematically, again, I'm mixing up between the two theories right now. I wrote the phi 4 Lagrangian up there, but I probably should have done the phi cubed Lagrangian. The point I want to make is that your diagram, your total blob will include the free plus the loops that you used to have, plus these fake new interaction terms. Okay. Now, when you compute the sum of blobs, and this is the key point, you're going to get this. Now remember, by the way, this diagram, you're using a new Lagrangian where m true is the thing in front of phi squared. So what you're going to get is, again, this sort of geometric series looking thing. Okay, and we're going to resum it using the geometric series just like before.
Just to clarify, sigma is the old like sum of all terms from, all the bubble terms, and now we have this new delta, which is the sum of all of the diagrams that are created by these counter terms, right?
Yes,
Or
so
like
I
counter diagrams?
technically I should have said like you can, this delta represent, just like how sigma for now it only represents this loop up to this degree in perturbation
Yeah.
theory. Delta m is the number you get from this specific diagram. It's just the number delta m. If you go to
Mhm.
higher order, what appears here will be more and more and more deltas in complicated sigma diagrams.
All right.
Yeah.
But it's the process that we're doing right now will be more or less similar, though, right?
Yes, exactly, exactly. If you go to higher orders, basically you're going to have more messy diagrams here, but that's it. And you
All right.
call all this stuff capital M squared, and it depends on p. Okay, now here is the really interesting step. You have, since you're using this Lagrangian that involves M true already, all of your lines already involve M true. So M true is already downstairs. And based on the KL spectral representation, this had better be equal to I over p squared minus m true squared. So what we have now is that we need this bracketed term to equal 0. Otherwise, we didn't put the right m true into our Lagrangian. Right? We'd be stupid if we said this is the true mass, but then when we computed the diagrams, you got a result that was p squared minus m true squared, or like if we got something like p squared minus 5 halves m true squared. Because then the true mass isn't what we said it isn't what we called the true mass, right? It would be stupid. So in order for our choice to make sense, so basically in order for us to have made a consistent definition of what the true mass is, we need to adjust delta m to make m squared 0 at p equals m squared. That way the pole is at m true. If it isn't, then the pole is somewhere else that isn't m true, And we've failed making an accurate definition of splitting our Lagrangian into the true mass and the other part because the pole is not at what we're calling the true mass. Okay, so this is one condition, and this will fix the value. It'll force delta M to take a certain value. And once you find the value of delta M, if you remember, we had defined M true as M bare squared plus like delta M, or maybe delta M squared, but schematically this is what it is. This is the same sort of relation found in another way. Once you find what delta M is, you'll find that if before in bare perturbation theory, let's pretend we computed it and we found this was the relation between the true mass and the Lagrangian mass. If you compute it in this way, you're going to get the exact same relationship. Okay, just two different ways to find out the relationship between the true mass and the mass that's in the Lagrangian. In one way, you computed diagrams and you circled things, identifying them as the true mass. In this case, you split the Lagrangian ahead of time, computed all the diagrams, and then adjusted delta M, which was the difference between the true mass and the Lagrangian mass, to make the pole fall at what you called the true mass. And that fixes the value of the counter term. This is how you can compute the value of the counter term. And similarly, in order to get the residue at the pole right, again, it's a little bit more mathematically complicated, but so for the residue of the pole, at P equals M true to have the right value, which again, since we're computing the correlator of phi true to phi true, where do I have it? I need it to have a 1 upstairs. So for the residue of the pole at P equals M true to have the needed / sensible value of 1, there's a condition you can make on delta Z, which actually didn't appear in my diagrams yet, but it should have. The condition will be that the derivative with respect to the Lorentz scalar p squared of the function m of the Lorentz scalar p squared, if you evaluate this derivative at p squared equals m squared, it must equal 0. And this gives you the proper numerator. Just once again to reiterate, if this weren't true, right, so this will fix the value of delta Z. If this weren't true, and we plugged in a different value of delta Z, we would find that the correlator had the form of this. At which point we would say we were dumb in picking our value of delta Z, because if we pick delta Z correctly, since we're doing correlation functions between phi true and phi true, if we pick delta Z correctly, we should only have a 1 in the numerator. If we don't, we have picked it incorrectly. We were kind of stupid in our choice. We didn't get the numerator that needs to be there when you have two phi trues.
Just to maybe, I don't know if this is necessarily a good question, but exactly why do we need to necessarily rescale our field?
Yeah.
It wasn't made totally clear why we're doing that.
Yeah, no, that's a good point. I can't say I'm totally clear on exactly why you want to rescale the field. Let me see if I can think of a quick explanation.
Because I feel like, we could leave Z as just Z. It wouldn't change, or maybe there is a reason.
No, I think this is more of a, I think it's more of a, I could be wrong, but I think it's more of a like conventional thing. Like it's very clear that you want the propagator to have a pole at the real mass. That's for sure.
Yeah.
But it's less clear why you would want to like massage your function to have residue one. I think it probably just is to do with convention of what you want, like a normalized, like in the basic wave mechanics sense, like a normalized field to have.
Mm-hmm.
But it's definitely less clear, and I'm not sure on it. But I don't think it's an important point.
All right, then. That's
Yeah.
fine.
What I want to make sure it makes sense though is it clear like why we need m squared to be 0 at p equals m true?
Yeah, I think that's very clear.
Yeah. Do you want to try explaining it back to me, maybe just for the listeners, so they have like someone who's learning it as well?
Well, I mean, basically, right, we want to make sure that our propagator has the correct mass shell, right?
Hmm.
And when we go ahead and calculate it with all our control terms, we get this extra m squared function.
Yeah.
And if, if our mass shell is to be, or I guess, using the language used, if our poles are going to be at, the true mass squared, then m has to be 0. Otherwise, our poles won't be in the correct spot, and that will move our particle
Yeah, yeah,
mass.
that's a good way to say it. If it isn't 0, the pole is going to be at a different place than what we called our true mass. So like it's not our true mass then, because the pole isn't there. That's a good way to say it. Yeah.
Yeah.
So this is the core idea of, and this is probably the key idea of like this whole thing, is that this is how you do renormalized PT, and that is the complementary viewpoint to what you can also do in bare perturbation theory. All right, let me do an example of this even so we can see how it works in practice.
Okay.
And it's worth me remarking that in order to make this happen, since sigma is infinite, delta m will also be infinite as well. But that is okay.
Yeah, it's fine.
And the reason that it is okay will, for this sort of the same reason, be that if you express your propagators in terms of m true, which is a measurable value, it's perfectly fine. All the other infinities are just from the fact that you were stupid in writing down the wrong number in your Lagrangian. All the quantities, if you express them instead of in terms of m0, if you express them in terms of m true, there are no infinities. Basically, it's the fact that m0 was problematic to begin with. m0 was infinite. It's just like a stepping stone. If you choose to trade m0 for m true everywhere, all the infinities go away.
That makes sense.
Yeah. Okay, so here's a real example where we compute the counter terms. So the example is going to be phi to the fourth theory. And again, we're going to do this in renormalized PT. We've already done it above for bare PT. And if we compute this sum of diagrams using the Lagrangian with like phi true squared plus m true squared. If we compute using that Lagrangian, we get that it is I, well, force us to check which diagrams we do. It's going to be the line plus I'm forgetting which diagram it is. Is it the cactus diagram? Or is that phi cubed? Well, there's some diagram with a loop in it, I forget. Plus a counter term diagram. And again, I'm going to draw a diagram that's oh no, it's the cactus diagram. That's what I was forgetting. Yeah. This is like the non-trivial loop inside of the four theory that occurs at one loop
Yeah,
order.
that makes sense.
So if you compute the sum of these diagrams, you get I over p squared minus m true squared minus some other stuff coming from these diagrams. They are sort of absorbed into m squared. Okay, and if you actually write down the value of m squared, again, m squared, you get it by evaluating these two things. It's minus I lambda over 2 times 4 pi times some horrible stuff plus I p squared delta z minus delta m. Okay? And again, if we compare this to this, we know it must take the form I over p squared minus m true squared if we've made consistent definitions of the true mass and the true size, like the true normalization of the field Z. So our conditions on m, just like before, are going to be that m squared evaluated at p equals 0 must be equal to 0. And that, if you plug in p equals 0 here, you're going to have 0 equals minus I lambda over 2, 4 pi times some horrible stuff. This term goes away. Okay, so that tells you that delta m is like I lambda over 2 times 4 pi. Or the i's cancel. It's like, I don't know. Again, I'm just doing schematics here, completely ignoring numbers. Oops. I think my pen is starting to glitch out seriously here. Can you see that on my taskbar too? The flickering?
Uh, yeah, I can. That's a bit strange.
It is a bit strange.
Probably not what intended feature.
Yeah, don't know what's going on here, folks. So that forces us to have our certain value of delta m, and that is the mass renormalization constant right there. Okay, next thing is we're going to take the derivative with respect to the quantity p squared as the variable. Let me see if maybe changing pens will work.
Well, the flickering stopped.
Yeah, I think I might actually have to take a break because my computer will overheat otherwise. And incidentally, what happens if you do this computation, is that you get 0 equals, and if you take the second derivative is just I times delta z. So that actually means delta z equals 0 for now.
Nice.
And again, this is just a coincidence in general, and if you compute it up to higher orders in lambda, it won't be 0, but for this set of diagrams, to this degree of precision, it is 0.
Okay.
So some people will say in words, at order lambda, the mass is renormalized, but the wave function is not renormalized to order lambda, meaning that there is no correction of size lambda to the wave function. And just one more time, it's like you don't actually observe delta m ever, like the true mass is what you care about. These are just the relations between the bare mass and the renormalized mass. You don't see them in your results, but they sort of inform you on the relationship between the real world variable and the Lagrangian variable.
Mm-hmm.
Okay, so let's take a break now because my computer is like a billion degrees. And honestly, maybe that might be all we do today.
That's fine. I mean, I think it was very informative, actually. Um, this, I think, I kind of understand what the whole renormalization perturbation approach is. That instead of going ahead and realizing that our M naught was wrong afterwards, we're gonna go ahead and try to like set conditions so that it's kind of like correct from the beginning in quotes.
Yes, that is a great way to say it.
And then basically the idea is that if it's correct from the beginning, then all those infinities just won't happen.
Yeah, that is exactly the idea. I
Of
can't
course,
even close my